Hello everybody. My name is Dmitry Krasnov I'm from the University of Ilmenau, and today I'm going to talk about our computing project PN68NI about thermally driven turbulence at low Prandtl numbers and strong magnetic fields. So before we get to the project itself, let me please tell you a few words about our research network that includes our university, TU Ilmenau, then the University of New York, University of Michigan, Dearborn, and two institutions from Moscow, Moscow Power Institute and the Joint Institute of High Temperature of the Russian Academy of Science. The project PI is Professor Jörg Schumacher, and here is the list of all the contributors to this project. So these are the research topics in the computing project. The topics include turbulent convection at very low Prandtl numbers, then magnetically induced instabilities in duct flows, so that's mixed convection, and finally wall modes at strong magnetic fields in thermal convection. So these are the applications that we target in our project, and the applications include solar convection with typical values of the Prandtl number of the order 10 to the minus 6, and cooling blankets or liquid metal cooling blankets for fusion reactors as shown here. So usually here they use lithium, liquid lithium, as a cooling media with typical Prandtl numbers of around 10 to the minus 2. So then we want to talk a little bit about the tools. So we are basically using two numerical tools. It's the NEC 5000 solver, which is based on spectral elements, and our in-house solver for incompressible fluids in rectangular and cylinder geometries, which is based on finite differences and can tackle mechanisms of thermal convection and magnetohydrodynamics. And finally, last but definitely not least, experimental facility with liquid mercury provided by our Moscow collaborators. So that's the physical model. So here we just show our physical model that includes pretty typical governing equations for incompressible fluids with momentum transport and temperature transport. You can see here there is an extra term responsible for magnetic effects, so the so-called Lorentz force term, and two additional equations for J currents, or electric currents J, and electric potential phi. So we use Boussinesq approximation and the so-called quasi-static model of electromagnetic interactions that assumes no induced magnetic field for these assumptions, like magnetic Reynolds and magnetic Prandtl numbers are much smaller than unity. And here are the control parameters like Prandtl number, Rayleigh number, Hartmann number that is responsible for magnetic field strength, and the aspect ratio of the cell. Done. For part 1, turbulent convection at low Prandtl numbers. I just want to list here a few simulations that we have done already with our finite difference solver for a rectangular box with a rather large aspect ratio of 25 for these range of Rayleigh and Prandtl numbers, and specifically I just maybe want to point to this run, which is the highest Rayleigh number we can access right now for this aspect ratio. So right now there is a simulation queued on SuperMUC that contributes to more than 400 billion points, and finally we want to upscale it to this resolution, which is going to be about 1 trillion points, and this is just to indicate that these sort of simulations are not very easy to do, and even targeting values of Prandtl number 10 to the minus 3 is already challenging, not to say about those observed for solar convection. So these are the flow fields for two cases of Rayleigh number 10 to the 5 and 10 to the 6. So visualized by the streamlines seated with 15,000 lines each. And here I just want to point to the characteristic width of the rolls, and specifically to the fact that we have investigated this point at a rather broad range of Rayleigh numbers for various Prandtl numbers that varied over 4 orders of magnitude. Then the temperature fields. So temperature fields are quite interesting because, as we can see, the contours, these contour plots are very blurry, and this is a clear indication that there is a very strong temperature diffusion. This is perfectly in line with a low heat transfer and low Nusselt numbers observed, which are essentially only slightly above unity for these Rayleigh numbers. Contrary to all that, the vertical velocity plot indicates that here we can observe highly inertial fluid turbulence, and we can even see vertical structures below the thermal boundary layer thickness. Basically, the resulting flow Reynolds number is very large, right? So, which is very nicely seen on this right insert, indicating just a zoom into a 1-to-1 region. Okay, so here we can see very small scale turbulence, but at the same time it all forms, let's say, a global pattern with very large structures which are otherwise would not be visible in a box of a smaller size. So, magnetically induced instabilities. This part of our project has been motivated by experimental findings, namely that upon increasing magnetic field, the flow does not really get laminar, which would be a commonly accepted point of view. But starting at a certain Hartmann number, the flow may instead exhibit some sort of fluctuations or large-scale fluctuations if we measure the temperature signal, as it has been shown in a number of experimental studies, and in particular by our Moscow collaborators. Depending on the heating, whether it's one-sided or two-sided, the flow could end up in the so-called quasi-random bursts or exhibit quasi-harmonic oscillations. And in our DNS, in our simulations, we just wanted to reproduce this, basically this facility at the highest possible accuracy, including honeycomb section, including the test section, including the real 3D magnetic field distribution, so basically to make our simulations as close as possible to the real experimental facility. So what was found? We actually found that, yes, the instability kicks in at a very similar Hartmann number, but it evolves differently depending on the heating asymmetry. For example, for one-side heating, it kicks in much earlier at one of the walls, basically at a warm wall. But in the case of two-side heating, the flow remains stable for a very long sort of time, and only at the very end of the duct the instability kicks in. In both cases, the flow evolves anisotropic quasi-2D structures elongated over the magnetic field direction. Quite interesting is that the signals of temperature measured experimentally and numerically almost collapse, as can be seen on the plots of time histories and on the power spectra. Then wall modes. So this is to check, is there any life beyond the stability limit? There is a stability limit that has been derived by Chandrasekhar, and basically it connects critical Rayleigh number with a Hartmann number beyond which no convection is expected at all. So basically convective motion should die. But it turns out that even if we go above the limit, the convection, yes, it dies out in the middle of the cell, but at the side walls it forms the so-called rotating, very thin, very flat rotating vortices, which are called basically as the wall modes. And even if we go far above the limit, so basically for Rayleigh number of 10 to the 7, the limiting value is around 1000. So if we go even far above this, they do not die, so they still keep rotating. And then we wanted to check whether is it possible to reproduce them in a cylinder cell, because the cylinder cell provides extra possibility for the statistical analysis due to its additional symmetry freedom. So as we can see, yes, these balls also appear here for the cylinder cell. They sit attached to the side walls, and even more, if we average this rotating motion in time, then it turns out that in the average sense there is also a region with negative convective heat flux here, for example. So conclusions. So first of all, it's worth to mention that turbulent convection at very low Prandtl numbers is highly inertial. Then characteristic width of the roll pattern saturates with decreasing Prandtl number T value that is larger than the critical wave number at onset of convection. Then we also managed to verify or to confirm experimental findings on magnetic convection, and that includes time signal, power spectra, and also limits of instability. Then theoretical predictions of a residual convective motion beyond the critical values of Hartmann number have been confirmed as well. So the wall modes form at the side walls parallel to magnetic field, both for cylinder and rectangular cells. The faster growth of Nusselt and Reynolds with Rayleigh in flows with strong magnetic fields is confirmed. So, and finally, let me please come up with our list of publications that have been published within the frame of this project, and of course let me please express our acknowledgements to Deutsche Forschungsgemeinschaft, National Science Foundation, Russian Foundation for Basic Research that supported this project financially, and of course Leibniz Rechenzentrum and Gauss Center for Supercomputing for providing computational facilities. Thank you very much.